It is easy to measure the potential of a dry cell battery. That is really a corrosion cell. By connecting the battery case metal to the common input of the meter and the carbon rod, the bottom, that's the case metal, carbon rod, which goes into the battery case, through which the energy is discharged to the red input of the meter. The voltage displayed on the screen is the potential energy in the battery. So that's that. That's easy. Everybody does that. Switch that one off. Right. In cathodic protection, we are seeking to acquire data using voltmeters that set their own zero on the common input, as there is no such thing as zero energy. We cannot measure the energy in all of the corrosion cells on a network of pipelines or tank bottoms because all of the anodes and cathodes are on the same piece of metal. We therefore cannot measure the amount of electricity coming out of the metal because of corrosion or the amount of electricity going into any particular cathode. We know this when we dig up a piece of rusty metal or excavate a pipeline. Commercial organisations suggest that we buy an item they call a half cell. Change that over. That is just a piece of copper in a solution of its own salts, and that we stick this into the ground and it magically becomes zero potential against which we can make a voltage measurement. We can see on the meter. Let's change this over again. And swapping over the connections to the half cell. Now we can see on the meter here that this is negative 155 millivolts. There is energy flowing through the meter, but when we connect the two inputs of the meter through a simple copper wire, like this one, there is nothing on the meter because there is no energy in the copper wire. Hope you can see the meter because of the light reflecting. And now one of the things has dropped out. That's right. So anyway, there's no energy in this copper wire and therefore we get zero on the meter. We go back to this one. Now let us connect a dry cell battery between the inputs, and we can see that the energy released by the corrosion reaction of the metal and the acid paste in the cell. So we could take, where did I put it? A dry cell battery. Lost it again. I've lost the dry cell battery that I had ready to connect here. Ah, here it is. Okay, so this is the dry cell battery, and this is the metal end. So this is the metal case, and we put this to the common, and we connect this to the wood, the electrolyte side of the half cell, so-called half cell. That is in series with the pipeline and the ground. The battery represents the reaction between the pipeline metal and the ground, so we connect the metal of the battery to the common pole of the meter and then to the porous wood of the half cell, and then the copper of the half cell to the input of the meter. We note the reading and then take the half cell out of the measuring circuit. We could do this simply by connecting this to this copper here. So this is the measuring circuit now, and we are measuring the battery potential alone, because the measuring circuit goes from here through the battery, through this copper to here. And if we reverse these connections, we can see that the battery value is positive. So in other words, this battery has this amount of charges, which is the electrical potential or voltage of this corrosion cell. Now what we could do is we could say, okay, supposing we have 4 batteries. That is to say, we have 4 corrosion cells in series, 4 sources of electrical energy in series, and we connect that through the half cell. What we are supposed to be able to evaluate through this system is the value of the voltage of one of these batteries. One battery represents the pipe to the ground electromotive force. This one could represent the telluric effects. This one could represent the stray current effects. And this one could represent the overhead power line ground effects. But using cathodic protection network procedures, we can identify and evaluate each one of these, but we still cannot extrapolate the value of the corrosion cell at the location on the pipeline that we are trying to investigate. We cannot ascertain if it is corroding by this measuring circuit, which is the only measuring circuit we can manage using the half cell copper sulfate, copper to copper sulfate ground contact electrode in the measuring circuit. It is of no value at all. And that is why I had to invent the Alexander cell. The Alexander cell is a corrosion cell in which we can measure the corrosion current and we can measure the potential at the anodic interface between the electrolyte and the metal. That is what we require according to the scientific method as determined and described in DIN 50918.